Hi everyone. Can you guys hear me? Okay. I'm Jin-Peng Liu. Currently a Simon's Quantum Postdoc Fellow, and today I would like to talk about my research agenda, quantum for science. Generally, quantum computation is a kind of cutting-edge techniques in the exciting area. So quantum computers is currently one specific device that can make use of quantum mechanical phenomena such as superposition and entanglement to perform certain computation. So this picture shows some current state-of-the-art quantum device we have. So the reasons that we're concerned with quantum computation is because they can significantly outperform classical computers for certain tasks. Here we know some potentially exponential speedups like integer factory, which is an NP problem, but we have polynomial type quantum algorithms. We also have some polynomial type quantum algorithms for quantum simulation and quantum linear algebra problems, which are B2B complete. So today I will focus on the quantum linear system solvers and their applications. So here is a very basic description of the algorithm. So suppose we are given a sparse n by n system where the sparsity is remarked as S is polylog in terms of dimension. So our goal is to produce a quantum encoding of the solution and proportional to the inverse solution. So the complexity of solving such a quantum state is scaled as polylogarithm in terms of dimension, which is a potentially exponential speedup in terms of n. So of course, we can generalize the algorithm to more other types of numerical linear algebra algorithms like SVD. So we have some knowledge of this of quantum linear algebra. However, and for potential quantum evolution in the future, we want to figure out what is the potential killer apps of quantum computers, and can we work on some the cutting-edge large-scale computation models, like how to model epidemic spreading, how to characterize the climate change, and even how to change large language models with applications like ChatGPT. And for these problems, and we have some fundamental challenges to deal with. The first challenge is about the large gap between the linearity of quantum mechanics to a nonlinear realistic systems. And the other challenges is in the engineering part, how to design an end-to-end settings to, for instance, how to interact classical data and quantum data. So actually, nonlinearity is essentially difficult in quantum computing if we really want to achieve an exponential speedup. So there are two reasons. One is that over the 20 years and the previous quantum algorithms and for nonlinear dynamics take exponential time, space, and time complexity. So there are some inefficiency in the previous design. In the complexity class series, and we also show some results over 20 years, like we know nonlinearities can imply polynomial type solutions for NP complete and even for Sharpe problems. So we expect that we cannot significantly solve the most general nonlinear problems. And for particular systems like strongly nonlinear Schrödinger equations, we can probably have some worst case type complexity explanation team. So our contribution is to partially resolve this problem in the weakly and dissipating nonlinear regime. So our contribution is to develop the first efficient quantum algorithm. Efficient means polynomial time for weakly dissipating nonlinear differential equations. We also established the almost tight lower bound to show the strongly nonlinear ones are generally intractable. So this is a paper published in PNAS, also with some first page coverage report in quantum. So here is a basic problem model, and we are focusing on a phototype quadratic ODE systems and with dimension n. So here the linear coupling matrix F is required to be the sort of sparse. Sparse means that all the real parts of eigenvalues should be negative. And for instance, if you are know about fluid dynamics, like the Navier-Stokes equation can satisfy less constraints. So given such a system, you can see F2 is a quadratic coupling, F1 is linear coupling, and F0 is a nonlinear inequality. So we want this system to be weightly nonlinear. That means we want F1 to be large and F2, F0 to be small. So we quantify these nonlinearities by the parameter R dividing here. So you can see, and the meaning of R is that the linear dissipation can dominate the nonlinearities as well as inhomogeneities if R is small. So a small R means a weak nonlinearity. So given that conditions, we developed so-called quantum color linearization methods. This linearization is totally different from all the previous linearization because previous algorithms only work on some locally truncation and linear system. But now we consider globally embedding and linearization techniques comes from infinity dimensional dynamical control. So the basic routine is that the first step is to embed an n-dimensional nonlinear ODE system into an infinity dimensional linear system. It's exact, but in the infinite dimension space. The second step is to properly truncate the system to obtain a poly n-dimensional system. And here, all the previous algorithms work on exponential n truncation, which is inefficient. And so given such a truncation, we prove the convergence rate given the previous condition R is more than 1. So R is essentially a convergence radius. So finally, and we can perform a quantum linear system algorithm for the linearized ODE and with compressed polynomials in N. So the overall complexity can scale as polynomial in N and polynomial in time. So here is the basis, the informal description of our theorem. So assume R is more than 1, we propose a quantum algorithm that can produce a quantum state exponential proportion to the final state and with complexity scaling poly in T and polynomial in terms of dimension. So independent of quantum computing, and we also, the contribution of improving the best known convergence of color linearization can also have some contribution in the classical nonlinear control series. So on the other side, we also show these results almost tight because we prove nearly tight lower bound results. So we have known when I is more than 1, there is this efficient quantum algorithm that we proposed. But if I is larger or smaller, larger or equal to square root of 2, and we also show a worst case instance such that any quantum algorithm must suffer from a worst case type complexity exponential in N. The base idea is described here, and so we call the amplifier. So we try to make use of the hardness of distinguishing non-orthogonal quantum states with a very basic lower bound techniques arising in quantum complexity series and is relevant to the so-called unstructured search. And on the other side, we also make use of a prime mass technique, the so-called butterfly effect. That means a small initial difference can result in a large variation. So we create such an amplifier, which is essentially is a nonlinear ODE that can change the small difference case to a large difference case. One case is hard to distinguish, the other case easy to distinguish. So actually the complexity of closing this amplifier is exponential in time. We also generalize these techniques to the quantum state discrimination problem, which is fundamental problems in the quantum complexity theory. So I also want to cover some brief applications of our algorithms and the theories. One large field is the so-called quantum scientific limitation. So, and the one result that we study is to apply our algorithms for fluid and plasma dynamics. We show some potential applications for simulating low Reynolds number laminar flows. And actually, Reynolds number is relevant to our parameter R. So I gave a same preliminary talk in annual meetings of APS division of fluid dynamics. So we also we're happy to see, and there are other applications that developed by others, like people using our algorithms to find the attractors and in control theory, and also study the reachability. And we can also apply our algorithms to simulate the pandemic spreading and also with the so-called SER model with rapid vaccination. And finally, we also study like the so-called predictor-prey cycles arising in economy and ecologies. So there are a bunch of applications that are developing right now. On the other side, and in one of my in preparation work, we also study the so-called applications in the quantum machine learning. So recall that our ambition is to make to change large language models by quantum computers. So here is a basic routine, like given a certain machine learning model, like you can define the laws and given training set and initial weights, and we just directly focus on a very standard gradient descent or stochastic gradient descent routine as here. So here we simply consider the MSE laws. One example is the multi-layer perception model. Like you can see, is all the polynomials of the different layers, and we vectorize all the parameters by the by theta in here. So the basic framework of the so-called quantum gradient descent is that we first perform the color linearization for the dissipated gradient dynamics, and then we have some certain guarantee that while the initial weights can be sparse, so we have efficient quantum state preparation routine. And then we also have some guarantee that while the model is sparse, so we can perform efficient quantum linear system solvers. Finally, we have some guarantee that while the output should be sparse, so we can perform efficient sparse state tomography to produce classical parameters. So this is total end-to-end classical to classical algorithm. So, and we try to argue that potential quantum advantage in the so-called fine tuning. That means that, so in the pre-training process of some certain large language models, unfortunately, the data structures and model structure are usually dense. But after some sparse pruning and in the certain fine tuning process, that we have some conditions that all the data sets and the structures can be sparse. And we also have some guarantee that while a certain system can be dissipated. So it's relevant to the so-called information bottleneck theory. That means when your system, including your brain or a computer, is actually learning things, you need to forget irrelevant information. So actually you can show the trace of the facial information matrix is higher and higher. Actually the matrix and together with its second order approximation, the Hessian matrix should have more positive modes. So that means the system is dissipating enough to help us to linearize. Secondly, we also have the lottery TT hypothesis to explain why the sparse tuning network can compete with the original network. So we have some numerical experience for either some small scale neural network applied to iris datasets, as well as the standard ResNet models with over 100 million parameters applied to CFAR dataset classification problems. Finally, I want to end up with my research agenda, and you can see I focus on the so-called quantum for science. I studied some fundamental problems from the quantum simulation to quantum algebra, and then I cross over the gap from linear to non-linearity to solve some nonlinear ODNs, PDEs with applications in nature science like the epidemic and fluid dynamics. Finally, I also developed an end-to-end design of the quantum gradient descent and with applications in sparse fine-tuning neural networks and toward potential applications to the large-scale machine learning models. So that's all. Thank you.
A quick question when Liji said so.
Oh, yes. So you started with a hello. You started with a linear system. You started with a linear system. Now, a linear system is easily solved. And then you turn into ODE. ODE is, I assume, is not solved easily by classical computers. What is the complexity of this ODE, known complexity?
Okay, that's a pretty good question. And first of all, and when you talk about the efficiently the hardness of solving system ODE, and I would say yes. So if we consider nonlinear ODE systems and the difficulty, and we have some very few guarantee, like we know it's P space or sharp P, and for the linear case is it should be much simpler, like it usually belong to P or B to P.
Maybe take it offline. Yeah. I had another question too for that. Yeah, thanks. Okay. So now we have a sequence of talks by